Okay, so let's introduce our Mr. Dr. Prashant Kumar Panigrahi, sir. Welcome, sir. Welcome to our this session.
Yeah,
And
thank you.
Dr.
Yeah,
Prashant Kumar Panigrahi, sir, is presently working as professor at Indian Institute of Science, Education and Research, Kolkata. Yes, sir, you are visible.
thank you.
IISER, West Bengal, India. He did his PhD in field theory from the University of Rochester, USA in 1988 and postdoctoral from University of Montreal, Canada and University of Illinois at Chicago in 1993 and 1990s respectively. He held teaching research positions at School of Physics, uh, UOH Hyderabad and PRL Ahmedabad. His research interests include quantum computation and quantum information, Bose-Einstein condensate, cold fermions, nonlinear dynamics, field theory, and wavelet transform. Professor Panigrahi has praiseworthy contribution in his research area, which includes more than 300 publications and distinguished uh, journals and conferences and book chapters. He has guided large number of summer interns at BS, MS level and is well recognized for his teaching. He was honored with elected Academy of Science and Referee for Physics Review Letters, Physical Review B, Journal of Physics, Pattern Recognition Letters, Physics Letter A, Paraman, European Physics Letters, etc. Now I request Panigrahi sir to take over the session. Please, sir.
Yeah, thank you. Thank you. I'm just sharing. How do I share?
Is it shared? What's up?
Is it shared?
So,
Yeah. Yeah, just 1 second. I'm entire screen. Yeah, I'm doing it. You just have a
yes,
patience.
sir. Yes, sir.
हाँ, सीधे क्लिक करा देंगे. Yeah. Yeah.
अच्छा है.
Just make it.
चल ना ठीक है.
Yes, sir. It's shared, sir.
Okay. Now is it okay?
Yes, sir.
Okay. Okay. So thank you so much. And so I see around 75 participants and a very broad all over India participation. So I don't know what is your background. So today what I'll be talking is very basic. If some of you do get interested, you have enormous number of avenues to play around. Like for example, IBM quantum computer is available. Many simulators, real quantum computers are available. If you're interested, for example, I have access to a 100-qubit simulator and also a real quantum computer. So we can also play around if you send me an email. So I will be, as I told you, I will be very, very big, emphasize on the basic aspect. But please remember that you don't need too much to play around. You learn basic things. Directly go to this, for example, IBM is the one platform which is readily available. You can do with their simulator. You can also go to the real IBM quantum computer and play around. That's the best way. And as Chandra pointed out, I started out as a theoretical physicist. When I went from Hyderabad University to Physical Research Laboratory of Ahmedabad in 2002, so they started this division on quantum optics and quantum information, which I was made the division head without knowing much about quantum technology or quantum computation. All of us learned on the road, and I remember I learned a lot from the students. Chandra was mentioning to a lot of students who have done summer project with me, including quite a few students from my Northeast, and I learned my quantum computation thanks to them. You can check my PK Panigale Google Scholar, you will find out most of my papers are with these BSc, MSc, BTech students. And believe it or not, quantum technology is for the youngsters. If you know matrices, you have the willingness to play around, you can contribute significantly. I'll show you how. So I'll be talking about quantum technology, and it's basically the technology of the 21st century, and why was it? So as you know, for example, most of our technology, starting from sending a rocket to Mars, to radio communication, optical fiber, all those things are based on only two laws. The first one is Newton's law, and as you know, there are three of them. Only quantitative law is the force. Mx double dot force is equal to mass times acceleration. And the second is Maxwell's equations that describes propagation of light. Only these two. Everything else, we are able to model it. And all technology that we have, almost all, are dependent on these classical things. So why is it that we are getting into the quantum domain, and why is it that it's becoming important in 21st century? So I hope to emphasize this point as I go along. So now you see, okay. So tell you first. I'll show you some recent progress because I told you that why did that. Now, for example, we are working up this possibility because quantum mechanics has been there since 1925. Heisenberg and Schrödinger wrote their papers in 1926. Dirac showed that the matrix mechanics of Heisenberg and wave mechanics of Schrödinger are identical. The interpretation was due to Born and others, statistical interpretation of quantum mechanics. I'll show you what is that. Dirac had a book in 1932, Principles of Quantum Mechanics. Nothing much has happened after that. Principles, but what quantum mechanics has thrown open are paradoxes. Famous EPR paradox. Then, entanglement, lot of counterintuitive behavior, and that has led to the development. So, believe it or not, principles, nothing much has happened. Principles, you see, 1932 book of Dirac, nothing much has happened. And what principle? Principle is simple solution of linear equations through matrices. So if you have solved linear equations, you know the matrices, you know quantum mechanics. Only thing little bit you have to know is called measurement. The so-called Copenhagen interpretation, collapse of the eigenfunction. I'll tell you about that. But this entanglement, again, if you know matrices, product of two matrices, direct product, or so-called tensor product, you will have encountered entanglement. Now, if you have, coming from the background of optics, you pretty much know what are these qubits. So therefore, from the very beginning, you cast aside any doubt if you have about mathematically being sophisticated to do quantum computation. Answer is no. Simple matrices, and simple matrices even now has enough amount of ambiguity and enough amount of questions still left open which you can contribute. So I'll show you some figures of recent progress, introduce you to quantum computation, and what kind of timeline, for example, next 10 years, what we're expecting, and beyond that, what you're expecting, where you should emphasize your energy. And the basic unit would be qubit. So obviously, I introduce you to qubit, because building a quantum computer requires understanding qubit and multiple qubits well. Now, when you talk about multiple qubits, superposition comes in. What is superposition? It is a wave property. See, for example, from the very beginning, there have been fight with particle nature and wave nature of light. Newton pointed out that particle could be corpuscles, particles. It could explain some aspect, the genius of Newton, otherwise he wouldn't have given the particle nature of light. So then came the wave nature, because certain things like superposition, diffraction, and interference, which people discovered even through experiment. Thomas Young and quite a bit number of people, they found out you need wave nature. There was a fight between wave particle duality, and finally, after quantum mechanics came into play, it was our de Broglie, Louis de Broglie pointed out that particle and wave nature are intrinsic to light and also intrinsic to any quantum particle, because of which he got Nobel Prize. Now, Einstein was the person who pointed out that you need particle nature to explain photoelectric effect. So for light, wave nature was there because of Maxwell equation, superposition, all of us are familiar. Particle nature came into play through photoelectric effect, for which of course Einstein got Nobel Prize, and it is a amazing thing is that it was just one equation, that half mv square, the energy of the electron that comes out is equal to h nu. H nu is the amount of light energy minus the work function. So in a metal, electron is bound, so you have to supply the work function amount of energy, and the light comes with h nu energy. H nu minus the work function is the energy that half mv square electron gets. Where particle nature comes in, more the number of photons, n h nu, n is the number of photons, same is the number of electrons. More photons means more intensity. But what was the ambiguous there, which wave nature could not explain, is you have to supply work function amount of energy. So if your frequency h nu is such that it is lower than work function, no photons, no electrons will come out. So no current until the energy of the photon is that of work function. That was the particle nature. Then more the intensity, more the number of electrons. That is how you needed a very simple equation and the genius of Einstein to explain photoelectric effect. And amazing thing is he got Nobel Prize for that. It was such a simple equation. Later on in life, for example, he gave many more complicated equations, special relativity, general relativity, whose properties we are investigating now, understanding now, like black holes. Yet we have to marry, general relativity with quantum mechanics. When special relativity was combined with quantum mechanics, thanks to Dirac, Paul and Maurice Dirac, we got antiparticles and many other things which have been experimentally verified. Now, so velocity of light is supreme. That also has a role in our quantum information theory. So the superposition, entanglement, those kind of things I emphasize. And don't get put off by the word entanglement. If you know hydrogen H2 molecule or helium with 2 electrons, singlet and triplet state of electrons, you know entanglement. Superposition you know very well because two waves when they superpose, you take E1 plus E2 mod square. So there is a cosine oscillating term. Intensity will oscillate between black and white, visibility. So these things you are familiar. Qubit is nothing but a column vector, 1, 0, 0, 1. Polarization or electron spin you represent with that. So, and these quantum gates are matrices. To our good luck, we need only 2 matrices, one 2 by 2 matrix, one 4 by 4 matrix. Now, if you are familiar with matrices, you know how to multiply matrices, you know a bit of MATLAB, you are in the game. Okay, and big simulators are available, simulate things, and what are the problems? I will tell you some of them. In fact, you will come up with more problems as you go along. But only thing you have to keep in mind that in quantum, certain aspects one has to keep in mind. Why is that? That also arises because everything quantum appears through unitary matrices. Quantum evolution, anything that changes the wave function is done through unitary matrices. Now, why unitary matrices? I leave it to you as a question, nothing very big deal, because in quantum mechanics, psi dagger psi is the quantity which is preserved in time. Psi dagger psi. You can see it is preserved in time provided the change is such that u dagger u is equal to 1. You change psi to u psi. Psi dagger will go to u dagger psi dagger. If psi dagger psi has to remain conserved, not change in time, u dagger u is equal to 1. That is how unitary matrix comes in to quantum mechanics. U dagger u has to be 1 because psi dagger psi probability has to be conserved. Now implication is that if everything has to be done through unitary matrices, certain things you cannot do. For example, no cloning. You cannot create Xerox files, exact replica of states, unknown states. You cannot hide information. You cannot, erase information. And these are the things which are consequences of very simple principle that everything has to be done by unitary matrices. You have to keep those consequences in mind, and then you can go ahead and design your algorithms. So now let me proceed. Okay. So as I told you, what are the advances which has taken place so that you people can go ahead and play around? Why you did it? So one thing is, you people are young. Many of you I can see are young members from all over India. Don't feel that you cannot contribute. Look at this teenage girl, Yuin Chan, 18-year-old. When she came, now she must be more older, and she came after summer school to Texas, University of Texas. and wanted to do a project on quantum computer because quantum computation was exciting. So his professor was very amused. You can see his professor's blog. If you go to his blog, Sorensen, 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 he writes nice blogs about recent developments. So he very amusingly said, see these MIT professors have come up with this thing called recommendation problem. A quantum computer can solve the recommendation problem very fast. I'll broadly tell you what is this problem. So this girl found out that these are all simple matrix problems, and he used an algorithm due to two Indians, one Professor Prakash from Cornell University, and lo and behold, she could solve it faster than a quantum computer. So and you search and find out or photograph you in Tang, and she became famous. Now she's probably pursuing her PhD or completed her PhD. So basically, matrices. The fact that matrices are the key players gives the power to the youngsters, and they can see the structure of matrices better than people like us having no idea. And therefore, don't do that. You can do fabulous things. You intend it, so can you. Now, another example. I'll show you, the pictures of Grover. Grover is an Indian from Punjab, and he was with IBM looking for search algorithm, powerful search algorithm. He found out, and he did not know much of quantum mechanics on his own admission. He only knew 2 by 2 matrices. So he came up with Grover search algorithm, which is one of the key algorithms that made quantum computation powerful, and because of which a lot of money is coming in. Another is source factorization algorithm. Factorization. 21 is equal to 7 times 3. He showed a quantum computer can do things faster. These two are established. I'll give you precise references. Okay, but yet people are now looking for problems which a quantum computer can do, a classical computer cannot do. So this is called quantum supremacy. So therefore, any problem you solve, everybody is trying to see what are the basic principles that are going in. Can a classical computer do it? Why is that? Because first of all, you have to really show quantum computer is required because it needs a lot of money. And philosophically also, one classical object emerged in a certain limit of the quantum mechanics. Why can't they do what quantum can do? So anybody says that I have done it through quantum and mine is better, there's always a question: is it really better? Classic example is this. So now, therefore, okay. Now, in India, for example, quite a few developments are taking place. For example, very recently, Professor R.P. Singh from our Physical Research Laboratory, you can go and search his website in PRL. They have demonstrated this is a project supported by ISRO, free space quantum communication, 300 meter, which is a baby step. If you look at China, for example, it's in terms of thousands of kilometers. So China has really made large progress. If you search PAN, you'll find out they have a satellite up there. There is a quantum optical fiber network between Beijing and Shanghai and other places operational. And quantum teleportation, quantum communication from Beijing to Austria, they have done it. You name it, they have done it. And a huge quantum computer with picture I'll show you using 700 lasers. If you just search PAN, all over the internet, you will find out what China is doing. And we are also taking steps because it has announced, I think, 8,000 crores in this quantum roadmap. So now this is one of the kind of technology which people are looking for, quantum communication. Whole world primarily is actually concentrating right now on communication problem. Why? Because quantum mechanics guarantees safety. Quantum cryptography is an active area of research. I'll tell you why, which is not possible in a classical world. So who are the leading players? You can do a bit of search. Almost all the places like ICERs, IITs, and everywhere in India, a lot of these youngsters, young faculty members, and some older ones also are into quantum computation in a big way. Now, even Government of India, for example, SIDAC, Pune, then in its centers in Calcutta and other places, there are active groups. Private, for example, TCS, IBM, of course, is a very big player, and ISRO, Department of MIT, Ministry of Information Technology, all of DST, SCRB, they're all funding quantum computation. So now, for example, RRI, Professor Urbasisina, you please go to our website. Very active researcher, many things are there. What I'm telling you is so-called quantum key distribution. And what is quantum key distribution? Two friends, Alice and Bob, they want to talk to each other. You must have seen, for example, you generate the OTP over data protocol, some number. That number is the key. Now that number has to be generated in a very secretive way so that between Alice and Bob, they would know the numbers, others will not know. That has been a challenge. And in 84, these two, Bennett from IBM and Brassard from University of Montreal, where I did my PhD, sorry, my postdoc, these two gentlemen sitting in Bangalore, they showed that through quantum you can do it, and that has become a big rage, 1984. Bennett, BB84, Bennett, Brassard 84. And honestly, it doesn't need except the understanding of the measurement, nothing more. Now, this is the key thing which people are implementing. Some only through measurement, some through entanglement. And quantum key distribution, you see, that is the rage all over the world. People are coming out with kits, selling it. Now in the market, you will find out UKD kits which are being sold around $8,000, $10,000. Okay, and goal is so that there is no mistake. Now suppose a classical computer usually don't have a mistake. OTP, for example, if some number is sent to you, 2798, if there's a mistake, then nothing will work. Only problem now with a quantum computer is a lot of errors. They believe that, next 10 years, there will be so much of error that we should come up with toolkits so that error is eliminated. So this era is called NISQ era. That, noise with a noisy environment, what kind of things you can do. For only small scale kind of quantum computation you can do. So this NISQ era is a noisy quantum computer is available to you. You have to do something using that. But things are definitely going to improve. Now, so I suggest that please take a look at Professor Ubersina's website. A lot more developments you will find out. Now, where are the whole world in this? For example, I give you one example. New to search, you'll find out many are there. Sydney, for example, is coming up with quantum computation network. Quantum computers to run Sydney's transport network. Quite fascinating. And so if you are football fans, which I'm sure many of you will know that 2010, I think, that football match in South Africa. Okay, that was the secure communication was through a quantum key distribution. I think that was the first time where in a game communication was done through a quantum network. Why did they do that? Because a lot of betting goes on, so they don't want anything to leak. So, and then many cities are now adopting optical fibers where through quantum communication, they are able to secure the message. So Sydney's transport network, why is it that a quantum computer can do it faster? Because of superposition, namely quantum parallel processing. Quantum mechanics allows you parallel processing. Okay, so now our neighbor Singapore, both universities, this NTU, Nanyang Technological University, and SNU, Singapore National University, both of them have very active, quantum programs. For example, there is this Quantum Science and Engineering Center, QSEC in NTU, installing of technology. Then you have a security Center for Quantum Technology. That's been there for quite some time. So they are really into many developed technology, some of which is probably going to see the market or has already seen the market. So now many of you can do your PhD if you want and collaborate with them also. They are open to collaboration. So now and okay. So for example, quantum key that is in this picture is key. So that it has now come to market. So these are many for example you can see this particularly China has developed this quantum technology. This Chinese company, for example, this quantum CTech, okay, and they are using it for finance. Okay, so quantum technology has really now come to reality. It is technological products that are out there in the market. Now, for example, what kind of things people are using. This is January, 20th January news. Because my students keep feeding me with this recent news, and some of our students are working here also as doctoral students. Now they are actually using silicon-based quantum processors. Because why is that? Because our regular regular processors are all silicon-based. It'd be good if we have a silicon-based quantum processor so that it fits in very nicely. so-called hybrid quantum computation can be done. Now, I'll get into those things a bit more, why initially people thought silicon would not do, now why they are coming back there. I'll tell you a little bit more. Now, what is a quantum computer? In a quantum computer, in some sense, is a very simple extension of a classical computer. You have the same circuitry. In a silicon chip, regular classical computer, what you have? You have these islands, silicon islands, which pictures, if you zoom microscope, you can see small things connected by wires. So those are actually, the smaller you make, the smaller your computer is. But the question is how small? That they realized in 70s that when the chip size became smaller and smaller, they encountered problem. So there was a law called Moore's law that they found out through experience.
এলাম শুনতে শুনতেই
They found out through experience that
হ্যাঁ ও
every 18 months, the chip size becomes half. What it means is that you can actually, if you keep the chip size same, double the amount of circuits you can draw. So it went on. But eventually, when this becomes smaller and smaller, the silicon islands become smaller and smaller. You have, what is the thing there? If you don't have anything, no voltage is applied, and it's called 0. If you apply 1 unit of voltage, it is called 1. So now, without any voltage, you have few number of electrons. You apply some voltage, those electrons are all excited into some level called, they have a higher energy, 1 electron volt. Let us say 0 and 1. But if you have few electrons, there will be a lot of noise. What will happen is that 0 may not look like 0. 0 may look like 1 because there is a lot of noise because of heating. So that is what they encountered. So there was a noisy circuit. They found out the noise is essentially coming because of quantum effect. And they, in fact, this person named Landauer, 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 gave very precise law. He pointed out that because of this noise, information is getting lost. And he pointed out in some measured quantity, 1 unit of information lost is creating half kT amount of heat. That's quite remarkable. Information loss is getting connected with heat. So statistical mechanics, thermodynamics, what we observe is really coming from very basic reason why the information is getting lost. We knew that thanks to Boltzmann that maximum entropy is equilibrium. When there is equilibrium, there is no order, only entropy when you maximize. So information, which is basically lack of information being entropy, and thermodynamics was known broadly. That is how we defined our microcanonical ensemble, canonical ensemble, grammy-canonical ensemble. But in a quantitative way, at the microscopic level, half kT is 1 unit of information. That was Landauer. Then, engineers always live on practical applications. There was this person called Toffoli. He said that, what can I do so that, this can be avoided? So he designed a gate called Toffoli gate. Where almost all their operations are done through this NAND or varieties of gates. So the Toffoli gate was producing no heat. They didn't understand why, but they used it. Then people later on found out that in a Toffoli gate is actually a unitary matrix. So it was not creating any heat because it was doing things through unitary transformation. That was appreciated much later. So without knowing, a person like Toffoli and many of these classical computer people, they have actually appreciated the power of quantum computers. Now, so in a quantum computer, what you do? In a register, you have the 0 and 1. Instead, you put matrices 1, 0, 0, 1. There are 2 matrices called qubit. So number 2 matrices, number 2 column vectors. So in classical computer, what you did? That was mathematics was given to us by Turing, Alan Turing, in whose name there are awards. You must have heard about Turing, who cracked this communication device, the Enigma code of the Germans, because of which claim is that Germany lost Second World War. So he was the person who gave the basic principles, Turing machine, how to design a computer, based on which real computers were designed by von Neumann during his atomic bomb project of Manhattan. So therefore, you have 0 and 1. So mathematics is 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 1 is 0. How do you do it? 0, as I told you, no voltage in a silicon island. 1 is some amount of voltage. How do you apply the voltage? Like a capacitor. You know how to apply voltage. Now we don't have to talk. We don't go to hardware. at the hardware level, that is what happens. Whenever it give a command, it changes 0 to 1, 1 to 0, 1, and whenever it hits 1 plus 1, 2, so there is a cutoff kind of thing, it brings it back to 0. So this is what it is. Mod 2 mathematics is the one which goes into our regular computer which we are dealing with. And Turing so that is enough. You can do everything. So we take our numbers, we break up into binary, write everything in terms of 0, 1, 1, 0, like that kind of thing. Feed it into a quantum register. All our operations are done through gates. And gate, what it does, either changes things or don't change things. And 1 plus 1 becomes 0. And that is how whole thing goes on. Now who looks at the hardware? We all do develop some software packages based on which, like MATLAB, Mathematica we use. But at the basic level, it is addition of real numbers, nothing more. But quantum needs complex numbers. And first of all, it matrices. That is how matrix mechanics came into play. So instead of 0, you put something called a ket 0, which I'll show you mathematically. It's a column vector, 1, 0. And so, and what happens is complex number comes in, superposition comes in, vector space comes in, because matrices have all these properties. Non-commuting properties comes in because matrices don't commute. All those things Heisenberg appreciated during the time when we were building quantum mechanics from classical mechanics. So these quantum states are which are coming into play. Once they come into play, these three key features, please remember: superposition, which gives rise to interference; parallel processing, quantum parallel processing; and entanglement. Entanglement truly gives quantum computer its power. These two, there is interrelationship between them. Superposition is necessary to create entanglement. They are the principles which comes in. But please remember, if you have purely wave like light, you can still use superposition interference. You can still do things without quantum. But entanglement is a quantum process. For example, you take 2 electrons in hydrogen molecule or 2 electrons in helium, they are actually entangled. What is the meaning of entanglement? I'll explain to you a little later. So now they can certainly solve some problems which started from 1994 integer factorization. Take a number, 21 is equal to 7 times 3. So Peter showed, a computer scientist, if you go to his website, you'll find out, he showed that a quantum computer can do it faster. And really faster. Instead of exponential thing, steps, it would do it in polynomial steps. That really became big news because I remember I had joined in Hyderabad University. Our computer science colleagues were talking about it. It apparently has become a big news. Why was it a big news? Because many of these algorithms, which are used for communication and cryptographic algorithms, they use on this integer, prime integer. Why is that? Well, you see, if multiplication of 2 prime integers is easy. 5 times 3 is 15. Well, suppose somebody gives you 15, asks you to find out the factors, becomes difficult. This, of course, is a small number, no problem. But if you have a big number, there are multiple factors to be there. To find each factor is not an easy task. And if the number is big, it takes almost age of the universe to find out all the factors. Therefore, these kind of objects where one step is easy, like multiplication is easy, but finding the factors is difficult, are used in cryptography. These are called one-way functions. For example, you use more sophisticated property of this elliptic curves, things like that. But the idea is this: one step is easy, the other step is difficult. Multiplication is easy, factorization is difficult. But Peter showed because of this superposition, exponential number of states are available to a quantum computer, it can actually do the factorization in polynomial time. Polynomial time is doable. So exponential is not doable, polynomial is doable. Computer science people classify the complexity of a problem, NP complex, this, that, through this. I am also new to it. Many of you who are doing quantum mechanics, they would know what are the NP complex problem and how much it can be solved. You talk to your computer science friend, mathematical physics friend, they will tell you these kind of problems. If you can solve one of them, you become very good, very famous, like Peter so did. So this branch, quantum computation, requires people to talk to each other, cross-fertilization idea. So now that was 94, integer factorization. It was very nice to see papers in big journals like Nature, Physical Evaluator with front page. 21 is equal to 7 times 3. Now you may ask, what is so big deal? 21 is equal to 7 times 3. And what kind of computers they are used? Those quantum computers are called NMR, nuclear magnetic resonance. In the beginning, NMRs all over the world were used as quantum computers. In fact, there is a good reason for that. They are actually initially came to physics, then this chemistry people are using, biology people are using. So by the time this quantum computation was coming, this biology people had huge, big NMRs. For example, if you are near in Bangalore, go to Indian Institute of Science, Professor Anil Kumar is the person who was the first person who did quantum computation using NMR in India. Many of his students are, for example, Professor Kavita Dorai in IISER Mohali, Professor Mahesh in IISER Pune, and our Professor Rangit Bhattacharya in IISER Kolkata. Many of his students are all over India doing quantum computer through NMR lessons. But as you must have realized that now NMRs are too bulky, so you can solve some in-principle problem, but you have to do something smarter. That is what the whole world is now doing. But it's quite funny to see these huge NMR machines being used to factorize a number like 15 or 21 and publishing in a prestigious journal called Nature. But that's how life was a few years back. Now you see, this person Feynman was the first person who understood the importance of quantum computation. In 1982, he wrote a paper. That was the year when I was doing my PhD. I started my PhD, and our professors used to talk about the paper. People thought that Feynman is crazy. So his emphasis was that, you see, if you want to solve a quantum problem, and he was specifically referring to quantum confinement in strong interaction, quantum QCD, quantum chromodynamics, which governs the quarks inside the proton. They are by that time found out experimentally that any amount of energy you do we supply, quarks cannot be freed from a proton or a neutron. But they are there. Experimentally, that when you hit that with electrons, it goes and hits three objects which are distinct. So there are three quarks inside the proton. But any amount of energy you give, even now also that problem is not solved. It is called confinement. Okay. And that problem, if you solve, you will really earn a lot of money. You can see it is one of those millionaire problems where a lot of money is involved. So it is confinement problem in quantum chromodynamics. So Feynman suggested that truly to solve some quantum mechanical problems, you should find out a quantum computer, because a classical computer cannot truly come up with that kind of algorithms. Okay, and he did it, used it, you showed it using path integral. What is path integral? So it's a very pictorially put. If you start from point A, you want to go to point B. In classical mechanics, you allow a path which minimizes the action. Delta S is equal to 0. So from point A to point B, you go by one path. Some sense becomes shortest, but delta S is equal to 0. Light also follows the same thing, Fermat's principle. It bends so that that there is a principle like that. Delta N, refractive index variation, becomes small. So this kind of shortest path kind of thing having been followed by physical particles. But when quantum mechanics came, following the idea of Dirac, it was Feynman who pointed out that in fact in a quantum principle, every path between A and B is allowed. So what is the difference? Difference is there a weight factor. A path is weighted, and that weight factor is exponential IS by H bar. S is the action. So for the first time, action became the key player. And amazingly, H bar has the dimension of action. Exponential has to be dimensionless. So exponential IS by H bar became the key factor in quantum mechanics, and it was thanks to Feynman's path integral. That was formulated following Dirac's idea, following the idea of diffusion process. For example, in classical diffusion, which gave rise to, this Einstein's work on, this diffusive processes, and later on mathematically Wiener's work, those same ideas were brought into quantum mechanics. So this so-called path integral showed that infinite number of paths are available between point and A and B, but weighted by a factor. If you go to far away from the classical path, is weight such that your contribution will become 0. By and large, the physical particle will follow the classical path, but quantum mechanics, all the paths are allowed. So that parallel processing was the one which Feynman was emphasizing. He said that you have actually many paths available. You can solve your problem by using many people. So quantum parallel processing. That was 82, Feynman. Paper was not getting published. So in fact, he met this editor of one journal called International Journal of Theoretical Physics, IJTP. When he heard about it, he said, why don't you send it to my journal? I'll publish it. So it was published there. At that time, it was not a very good journal. Then came 1985, David Hughes. He got into, following Turing. This is actually Turing, not tuning. So being an Englishman, he sort of, formalized it. He said Turing developed, classical computation through this mod 2 mathematics. 0 and 1, 1 plus 1 is 0. Now, similarly, universal quantum computation, can it be done? So he showed that indeed it can be done. So there is a quantum Turing machine. And you can actually design through quantum circuits. And to his good luck, he pointed out that quantum is much simpler. You need only two matrices. You have to do through matrices and need two matrices, Hadamard and control knot. So those are the theoretical developments. 1981 was the time when no cloning theorem was discovered by Jurek and Wouters. That through unitary matrices you cannot clone, you cannot create Xerox copies of unknown state. Now in 1994, as I mentioned to you, it was Peter Shor who used this quantum algorithm to factorize that numbers in polynomial type. And who is the middle person? Middle person is the one, our Paul Adrian, middle person is de Broglie, Louis de Broglie. A very simple philosophical work that every particle will behave like a wave, every wave will behave like a particle, wave-particle duality, which is now being used. When you measure quanta of light, so that's like particle nature. As it propagates like a wave. You see diffraction, interference, and parallel processing. So it's a very philosophically beautiful idea, combining in the centuries of fight between corpuscular theory and wave theory. Newton and Young, Thomas Young, the group of people, and coming up with this thing, which was very powerfully used by Peter Shor. Very good. So now we have now crossed 90s. Okay. So I always mentioned Professor Dr. Grover because amazing person, very simple man, and in his own understanding, he showed that a quantum computer can search an unstructured database very fast. Mathematically, the problem is very simple. It's a matrix problem. And, his thing is that a regular computer can do it in order n step. Here it is only order root n. In some sense, it is not a big development because Peter showed exponential to polynomial. If you like his paper, just go through his paper. Very readable paper, but, I'm not a computer scientist person. But you talk to your computer science people, you'll be able to read, go to your site. But Grover's thing is a very simple one. You start from some matrix, like 1, 1, 1, 1 column vector. You want at the end only one of them. So it could be like 0, 1, everything is 0. So you apply n by n matrix, you'll be able to convert from there to here. Unstructured database is given by that column vector with 1 by root n, 1, 1, 1, 1, 1, everybody is 1. And you are looking for one state which could be like 1, everything 0. How do you go from here to here? Obviously, you apply n by n matrix, you will do it. But n by n matrix, if you do, matrix multiplication will take you n square steps. So order n square, and that becomes bigger and bigger. What Grover pointed out that you can use something called, divide and rule. Do everything in 2 by 2, 2 by 2, 2 by 2 steps. Very beautiful. And in the process, what happens is that you use superposition. Because if you look at 1 by root n, all ones, they can be thought of as superposition of 1 by root n, 1, everything 0, plus 1 by root 1, root n, 0, 1, everything 0. So this column vector, 1 by root n, everything 1, can be thought of as superposition of n vectors. They're all column vectors. So through, you know what you are looking for. That you feed into your algorithm. So you search, giving that I'm looking for the state, let us say 1, everything 0. So what the algorithm does, that it does mirror reflection around that. You don't change that state. Other states you employ parity, put in a minus sign. So what it does is that it slowly, through interference, kills off the other states so that your state converges to the state we are looking for, 1, 0, 0, 0. So you can see interference, the so-called wave nature is used to introduce minus sign through parity to kill off other states except the one which you are looking for. The one which you are looking for goes into such a matrices called oracle. Essentially, you reflect around that so that that one does not change, rest changes. Very readable. If you go to Wikipedia, you are able to read it. Very, very readable thing. And dividing and rule principle was used in fast Fourier transform. In fast Fourier transform, again you have a column vector. You do a Fourier transform, means you are applying an n by n matrix. That n by n matrix is made out of roots of unity, okay, called Van der Mold matrix, and you come, it's an inversion problem. Inverse Fourier transform is inversion of that. But then, you can actually do it faster if you do 2 by 2. And that apparently was known to Gauss, but in 66, it was Coolidge and Tukey who showed fast Fourier transform, and that made industry wake up, and industry started using Fourier transform to design beautiful products like cars, and smooth looking cars, aeroplanes. All the smooth looking sort of objects were designed using Fourier transform. So if you see the technologies of the 20th century which changed the world, we'll find out that this fast Fourier transform is mentioned there. So Grover algorithm is similar. Instead of doing n by n and think directly, you break it up into 2 by 2, 2 by 2, give the input of the thing which you're looking for. Around that, do suitable operations like parity, so that you kill off the others where superposition principle comes in, and you are finding about your answer. So these two, 1994, it was source factorization, which also used Fourier transform. Why am I emphasizing Fourier transform? Because if you read source paper, it uses Fourier transform. Very simple, nice mathematics. And Fourier transform, fast Fourier transform uses 2 by 2 matrices. Grover's thing uses 2 by 2 matrices. I'm pretty sure if you play around with these two, you can still make come up with some novel ideas, because Fourier transform has a lot of things to offer. Very good. So these two really brought, quantum computation during my time when I was in Hyderabad. People are waking up to quantum computer. Who are the people who are funding? Without funding, you cannot do much. In USA, a lot of money came through defense and so-called DARPA project. And because defense was looking for secret communication. Now, Europe, for example, a lot of money came from Swiss bank because banking sector needed quantum communication to be done in a very secret way. So there are the people, a lot of funding started coming for research. Right. Now, what is the mathematics? Mathematics, if you see, for example, Peter's source thing, they're all matrices, nothing but matrices. Every big matrix can be built out of a small vector called 2 by 2 matrix and column vector called 0, 1, 1. You take direct product of 0, which is a column vector called 1, 0, 1, which is 0, 1. You can build all big fellows. So it's like a brick. 2 bricks makes everything. So building blocks 1, 0, 0, 1. And you can add them up, that is called superposition. Okay, if you know for example, vector A, you can always find out its component, I times AX plus J times AY plus K times AZ, if there are 3 vectors I, J, K. Now you also know I, J, K are unit vectors along X, Y, and Z direction. I square is equal to 1, J square is equal to 1, K square is equal to 1, they are unit vectors. I dot J is equal to 0 because the angle between them is 90 degrees, they are orthogonal. So in 3 dimensions, you need 3 of them. Now in 2 dimensions, the example is here, 0, 1, 1. They are also vectors, pretty much like I and J. So 0 is a column vector, 1, 0. So when you say I square is equal to 1, in matrix language, it would amount to dagger, which will take a bra vector. So I'll show you the notation. This is due to Dirac, this is called a ket. Now dagger of that is called a bra. Normalization is 0, 0 is equal to 1. 1, 1 is equal to 1, and they're orthogonal. So 0 times 1 will be 0. Now, why do you normalize it? Because a physical particle, if it is there, we normalize it to 1, indicating that it is there. Okay. So this is the thing what we are looking for. Every quantum computer in the market is built at the basic level by this 0 and 1. So difference between a classical and a quantum is classical thing. This is a number. This is also a number. And they are created by no voltage and some voltage. Here these are matrices. Now how do you create it? So you need any physical system having 2 qubits, 2 levels. It can be 2 electrons, ground state plus excited state. It can be superconducting qubit. I mean, 2 levels, 0 and 1. Essentially 2 levels. The moment you have 2 levels, you have two electrons. You 1 electron will spin up and down. Photon with polarization, 2 polarization. You give me 2 states, and you have a building block of qubit. So silicon, for example, people are looking for quantum dot. They have 2 levels. What are those types people are now using in the market? Superconducting qubit is the most familiar one. IBM and many other object computers people use. Quantum dot, I showed you this so Australian Sydney group, they're using quantum dot, many of them, Europe also. Trapped ion, physical ions, you trap them. They repair each other because of which, in some sense, they gain stability. 20 qubit ion quantum computer is available in the market. For example, MIT, if you see, has given access to many faculty in India to ion quantum computers, which are there in the market, 20 qubit. So through your faculty, you can actually do. So ministry gives money for user time, and you can actually put problems, and these are all in the market. Photonic qubit system has not come to the market yet, but people are working on it. But they are used for communication. For example, quantum key distribution, many of the quantum communication protocols depends on light, local photonic qubits. Now, and nitrogen defect in diamond has become very popular now if you search. Nitrogen defect in diamond. So they call defect-based qubit. Why are they very popular? Because they are robust against noise. Somehow, those kind of defect, nitrogen defect, don't get affected by noise. Now, in future, topological qubit. Why topology? For example, topological objects are not easy to be altered. As you know, for example, football, and South Indian Vada and North Indian Vada. They are topologically two distinct objects. Why is that? Because North Indian Vada, is a rounded object. Whole surface is a sphere. Whereas the South Indian Vada has, this topology of a donut. You, by no way, you can change one to the other continuously without hearing it. So they are topologically two distinct objects. Now, those kind of things, if we can make them into qubit, they'll be robust because topology changing will require the whole thing to change. And that is not easy by noise. So Microsoft actually put a lot of money into topological qubit. It suffered a little bit when they were trying to use Majorana fermions for this. So Majorana, that experiment in Europe, there were some problems. They had to withdraw that paper. This DTU, Denmark Technological University, which because of which, but eventually probably some form of this kind of thing will come because they are very robust. And noise is a big problem. And as I told you, NMR qubits were the ones which are fast used. Please look at website of Professor Anil Kumar. You'll find out he was the beginner in India. Ori from MIT was the guy who started it. And all over the world, even now also, people are using NMR, nuclear magnetic resonance qubit, for quantum computation, showing many nice ideas. For example, I had an idea which Professor Anil Kumar verified. I'll show you what was that. But slowly, because these things are big, it is getting out of things, other things are slowly coming in. So as I told you, it is this 0 and 1 who are the building blocks. They are called qubit. They are matrices. The notation is due to Dirac. This flow is a column vector 1, 0. This flow is 0, 1. These simplest building blocks, they are like the two bricks. But the good thing is that they are vectors. So you can superpose them. And as I told you in quantum mechanics, complex numbers comes in, alpha and beta. So psi mod psi must be 1 because one electron is there or one photon is there, depending on what it represents. And you see the superposition. The parallel processing comes because of superposition. Wave nature. Now this mod size equal to 1 gives you the condition. So because of which alpha beta has to satisfy certain conditions. And please remember one thing, that in quantum mechanics, mod size, namely psi dagger psi is physical. Therefore, overall phase, if you put exponential I theta, if you take dagger, if you exponential minus I theta, they will cancel out. Therefore, one overall phase is not measurable in quantum mechanics. But relative phase, if there is a sign here, if you put minus, that you can measure because that minus sign is between 0 and 1. So relative phase is measurable through interference experiment, overall phase not. And quantum mechanics will satisfy will satisfy some conditions like this. That you keep in mind. Okay, very nice. Now, just give me a second. Hello, I'll call you back. Hello. Yeah. 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 By now, are there any questions people would like to ask? Any questions? Okay. You people are able to hear me, right? Am I audible?
Yes, sir.
Yes, sir.
Yes, sir. Yes, sir. You're audible.
Okay. Good. 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 So now, so what did we say? That we are using the elementary building blocks, which are just simple matrices, column vectors. But going from number to column vector has brought in a very interesting idea called vectors. And we are all familiar with matrices because the linear equation when you solve, we encounter matrices. So mathematically, complex numbers, matrices are the ones which are. Therefore, if you use MATLAB or Mathematica or Python, you can in fact design a quantum simulator without getting into any problem. Okay, so if you know matrices, you are into it. Like one more thing I'd explain to you. That, for example, as I told you, these qubit are two-level systems. There could be two levels of the electron. Now, superposition is this, that like a bond between 0 and 1, you create a state 0 plus 1. That gives you parallel processing, and everywhere you encounter it. Now, before we go there, let me explain to you what is another aspect of quantum mechanics called measurement. Suppose if you take 0 plus 1, this state, if you measure and try to find out, is it the state in 0 or is it the state 1? So that means when you have a superposition, you are finding out the basis state in which you are measuring. 0 and 1 are like the spin along the z direction. You will find out that after measurement, the 0 plus 1 will go to 0 or 1. So that is a very uniquely quantum. Measurement is affecting the state. The state initially was 0 plus 1. Now the state has become either 0 or 1. And now which one? That we do not know. Okay, and if I normalize it, I'll put 1 by root 2 here, 1 by root 2 here. And this state 0 plus 1, if some of you are familiar, is actually the electron spin along the x direction. We have three directions, z, x, and y. In z direction, it is 0 and 1. In x direction, it is 0 plus 1 and 0 minus 1. One is plus x direction, one is minus x direction. 0 plus 1, 0 is along plus z, 1 is along minus z. The two states. But if you think for a moment, you will see it is very counterintuitive because this state is along the x direction, 0 plus 1, positive x direction. Now it takes 90 degree to z direction. If it's a classical object, I will find that the vector is pointing along x direction. The component along z would be 0 because cosine 90 is 0. That is what we have been taught. A is equal to I times ax plus j times ay plus k times az. If I want to know what is along x direction, I'll take I, dot it with a, I dot a, and it will give you x, because I square is equal to 1, I dot j is equal to 0, I dot k is equal to 0. Similarly, this vector is along x direction. I told you 0 plus 1 is positive x, 0 minus 1 is negative x. And 0 and 1 are along z directions, positive z, negative z. Angle is 90 degree. Classically, I would have expected no component. But note, this is the first counterintuitive, amazing feature of quantum mechanics, that even if it's along x direction, if I choose the basis and measure it along z direction, I'll find it there because particle is not lost. Measurement does not kill the particle. Particle has to be there. So either 0 or 1 is completely arbitrary. I do not know which one. So if you think this is trivial, this is actually the most powerful thing. It has generated a machine called quantum random number generator. You can randomly generate numbers, random number generator. In the industry, there is a big requirement for random number generation. If you see MATLAB, there is a command /rand, R-A-N-D, which generates so-called pseudo-random numbers. There has been no random number generator in classical world. First time a quantum computer gave you a quantum random number generator. It is truly quantum. It's truly quantum because measurement leads to collapse of the state. So this object, 0 plus 1, either going to 0 or 1, is called collapse of the wave function. This was due to Niels Bohr and Copenhagen interpretation. Particle is not lost. Now, the amazing thing is that you should play around with it. state 0 plus 1 is along the x direction. If you take 0 plus I times 1, it will be along y direction. If you take the vector along y direction, which has an I, you measure along x direction or z direction, you will be able to find it. Either it will be 0 and 1. Okay, so only thing is if you do thousands of measurements, large number of measurements, you will find 50% is 0, 50% is 1. Half the time it is along positive direction and half the time along negative direction. So therefore, the spin value, if it is positive along positive z, negative along negative z, 50% positive, 50% negative, it will be 0. And that's what I was expecting as the answer because my state is along the x direction, 0 plus 1. If I find what is value along the direction, I should find 0. So in quantum mechanics, classical answer emerges in a statistical manner. You do large number of measurements and 50% of the time you will find out, it is along some direction. Why 50% here? Because 0 plus 1. In fact, I want to normalize it. I should put it 1 by root 2 0 plus 1 by root 2 1. 1 by root 2 is the probability amplitude. Square of that is the probability. Classically, we knew about probability. For example, classical statistics deals with probability. Coin tossing, when you do, it deals with probability. But quantum mechanically, it is probability amplitude. So that's the difference between quantum and classical. So this took a while to understand. For example, Niels Bohr Institute Copenhagen played a very key role. People like Jordan and others played a key role in Bohr, Max Bohr in statistical interpretation of quantum mechanics. And so far, all these things have been found to be true. So collapse of the wave function, 0 plus 1 going to 0 and 1 completely randomly, has been found many, many times. We have now generated a technology called quantum random number generator. If you are curious, you'll find out from USA, they are broadcasting random number every day. So how they do it? There's a JILA, there's an institute called JILA, J-I-L-A. So you search for J-I-L-A, you'll find out from there they do the experiment, this kind of experiment, generate random numbers and broadcast it. Who uses it? If you are doing Monte Carlo simulation, you need random number. So therefore, collapse of the wave function, this I am emphasizing because it is uniquely quantum. This was the fact which was used for BB84, Bennett Brassard 84, for quantum key distribution. Why was it? Suppose you are communicating through the state 0 plus 1. Now somebody is trying to find out what you are communicating through it. And he or she, usually it is C, Eve, measures in the basis 0 and 1. But what will happen? What will happen is the state 0 plus 1 is going to change to 0 or 1. So therefore, when Eve has looked into it, the state has changed. And that is quantum mechanics. A measurement changes the state. That has no analog in classical world. So therefore, if in the quantum world, you will be able to detect that the Eve trying to find out what you are doing. That was the idea of BB84. And believe it or not, they were in Bangalore attending a conference. They heard, this behavior of the quantum particle, and over a glass of beer, they thought about this algorithm. It is really true. Bennett Brassard 84 came out, and it is, you see, the power of a single qubit superposition and measurement leading to collapse has generated the fast technology, quantum random number generator. And many more may come. It's up to your imagination. What can you do with superposition and measurement? But people have come out with computational algorithms, that measurement-based quantum computation, which is uniquely quantum. You measure the state, you collapse. But you can use this for computation, measurement-based quantum computation. It's somewhat like, you ask, is it true? Answer is no. So through yes, no, yes, no, yes, no, you are able to come up with the answer. Something like that. So if you are curious, you can search to Wikipedia and find out measurement-based quantum computation. It's a uniquely quantum algorithm. It's based on measurement leading to collapse of the state. And who would have thought that it will give rise to computational power? Because there is some arbitrariness here. 0 plus 1 is going to 0 or 1. State is collapsing. But yet it is useful. So therefore, you should play around with it, because if you talk to others who are not physicists, they will say, measurement is so uncertain. It gives rise to completely uncertain answer. How do you use it for something like computation which is very certain? But the answer is that even if it is uncertain, on the average, if you do large number of times, you will get probabilistically things which are reliable, which are closer to truth. For example, Grover search, if you see, it is not deterministic. Probabilistically will converge on the answer. but so large that you know it would be like the thing what you are looking for. If you are looking for the factors of 21, which is 7 times 3, answer will converge to 7 and 3. It is not exactly delta function. So that is what the quantum world is all about. Measurement, collapse of the wave function. Collapse is completely arbitrary. We know which is this new Copenhagen interpretation of quantum mechanics. So you are starting with a spin along x direction or y direction. If you measure along x, you will find the spin is along x. It could be positive x or could be negative x. If it is along y, if you measure along z, it would be along there positive z or negative z. So if you tell this thing to your friends who are not into quantum world, they will be surprised. This is what nonsense you are talking about. Your thing is along y direction. How could it have a component along x direction? Now suppose if I agree, then how could it have a component along z direction? But it is the strange property of the quantum world, which is very, very useful and very counterintuitive. That gives quantum computer the power. You have to deal with it. Now, what is another thing? So that was basically measurement and superposition. That gave rise to the miracle which I talked about. It is this thing about entanglement. You take a singlet state. For example, we have encountered singlet states, triplet states in physics. Einstein was talking about similar kind of states. So, for example, I'll give you the physical picture of that. He pointed out that gives rise to some kind of a non-locality, which is very strange because you can do some measurement in Delhi, you can affect the state in Washington. And Einstein somehow didn't like it, that this kind of non-locality is a fault of quantum mechanics. Okay. So this kind of correlation, non-local correlation, what led to big debate. So, for example, Einstein thought about the experiment we using a harmonic oscillator type of variables called continuous variables. It was Bohm who in 50s pointed out that you can do it using spin matrices, 2-item matrices. And that's what Bell used in 60s to show that this leads to a quantification of quantum principle or quantum product. In specifically, he showed there is an inequality. Certain object, if you measure, if it is classical, it should lie between 2 and minus 2. If it's quantum, it should be 2 root 2 to minus 2 root 2. Experimentally, in 80s, they started verifying it. And they found it is always between 2 root 2 to minus 2 root 2. So quantification of this kind of non-local correlation led to many interesting things. Okay, that was very interesting. So there was no development in book writing. It was basically these confusions or paradoxes and coming up with experiments to prove it. And those days they are not thinking about using it. So then this 1993, this property of entanglement was used by engineers. You can again see and find Bennett, Brassard, quite a few, 5 or 6 of them, they showed the same counterintuitive property can be used to teleport, which we have seen in Star Wars. Now, teleportation is the reality. First experiments were done using 90s, 97, 98 to show that teleportation is there. It can be done. Now you can teleport at huge distances across the Danube, through the satellite, from Tibet to Beijing. You can actually teleport states. And you know what you are actually doing. You are actually not, state is not going, information is being teleported and state is created on the other side. And this is exact. In this non-local property called entanglement plays the key role. So I hope that you appreciate this entanglement. This is truly non-classical. And what is this non-local correlation? So let me show you this experiment. Suppose there is a source, like in Bombay, for example, a reactor that produces pi naught results. So the pi naught, for example, could be in a state like this. Actually, it is not exactly in this state. It is xy plus yx, but for illustration, let me say xx, yy. So these are binary variables. It could be 1 minus 1 or 0 or 1. So this object is 0, 0 plus 1, 1. This is one of the Bell state. Another Bell state is 0, 0 minus 1, 1. This is a matrix product. So for example, it is 0 means 1, 0. So 1, 0, direct product 1, 0 becomes a column vector with 4 entities, 1, 0, 0, 0. This fellow becomes 0, 1, direct product with 0, 1 becomes 0, 0, 0, 1. This superposition. So it is 1 by root 2, 1, 0, 0, 1. So this is the mathematics. Suppose this state was produced, which can be produced in a reactor, and it decays. Pi naught will decay into 2 photons. So Bombay, one is going towards Australia, one is going towards Latin America. So you measure, for example, in Miami, the state. This flow is measured in, somewhere in Australia, far, far away. But amazing thing is the moment you measure, this is what is implementing. This is the measurement apparatus A and B. If it is +1 here, it will be +1 here. How do you check? Through the correlation measurement. Okay. If it is -1, you will find -1. Why is that? Because it is 1, 1, this is -1, -1. Okay, so this is the kind of thing, coincidence detector, which has been used to show this thing is really true. Now, it's very counterintuitive because these fellows could be far away from each other. One could be, for example, here is Bombay, here is Australia, and here is Latin America. Now, people first of all showed that this correlation is there. EPR, correlation is there. It is non-local. You cannot use it to send information faster than light. So keep in mind that information speed is always maximum light. For this non-local correlation is instantaneous. Very counterintuitive. Moment you measure this fellow, if it is 1, the other fellow collapses to 1. If it is -1, it collapses to -1. What is the meaning of collapse? Because after measurement, the superposition fellow will go down to either XX or YY. Superposition is lost, becomes one state, XX or YY. So this experiment is the key to quantum correlation, collapse of the wave function, Bell inequality, and is being probed even now. So you reflect about it. Now, forget about these principles of quantum mechanics. Private companies are very much in market. Now, many simulators, for example, IBM has both simulator and also quantum computer, physical ones, multiple of them, 5 qubit, 16 qubit, 20 qubit. Rigetti has simulator, many of them. Microsoft, Google has a processor, and they showed Supremacy, made big news. And so many, D-Wave has been there in Canada for quite some time. There's a lot of debate about what they have, is it really quantum computer or not. People actually showed, that it is actually a quantum computer. That led to a lot of developments. What is a quantum computer? So it has a brain, is a processor, superconducting qubit, is a processor. It could be, is hidden inside this silicon chip, but inside it is actually a superconducting qubit, somewhere here. Lot of wires going on to connect to electronics. If you look at the IBM machine, it looks like this. So now all this heart keeps on pumping, broad kind of thing. So basically, liquid helium, which goes around, keeps it cool, like our blood. Without that, there will be problem. So liquid helium, very low temperature, and then you have to some skeleton has to be there to protect it. They are these skeletons. We have gold plate. So pretty much the machine looks like that. You have to cool it down to at very low temperature. Okay, and outside that has to be cell like your skin. So that kind of structures you see very big ones, like all the computers, very big machines. And that is how they are available, accessible. You can do quantum computer. In fact, sitting in Mohanpur, we have done it. Quantum check, many other things using that. First, you load it to a simulator, check that it works. Then later on, you can they will allow you to do it on a real quantum computer. If you collaborate with them, they will give you access, if the problem is good, to big quantum computers. Otherwise, you can have access to noisy ones, up to 16. But simulator is any. Okay, so now so quantum logic gate are only two matrices, Hadamard and controller. Let me show you that. They were sort of thought about it starting from 70s, but now only people are using it. What are these Hadamard gate? It creates for you superposition. This is a matrix 1 by root 2, 1, 1, 1, 1, 1 minus 1. Creates superposition. Starts from 0, creates 0 plus 1 by root 2. Starts from 1, creates 0 minus 1 by root 2. This is a single qubit weight because it acts on 0 or 1. So anywhere you see a configuration, it will look like this. A single qubit will be like this. Apply Hadamard like this and change. So this is one which creates linear superposition because that is what you need. Now there is another one called control knot. So it is denoted like this. There are two lines, two particles. This flow is controlling this flow. If this flow is 0, nothing will happen here. If this flow is 1, things will change here. You see, B is 0, A is 0, nothing happens. B is 1, B is 1. If this flow is 0, you can see it has changed now. B remains intact. This flow has become 1. B is 0, this flow is 1, nothing happens. 0 is 1. If it is 1, it becomes 0. Control not. These are the only two things you need in a quantum computer to beat everything. Control not and RMR. That's all, nothing more. This flow creates entanglement, this flow creates superposition. So as I told you, Toffoli without knowing came up with this 3-qubit flow, which now we realized is actually control not. These two flows are controlling this flow. And using that, he was able to do computation pretty much like classical one, and it was reversible. Now if you see the matrix, that matrix is unitary, because of which only it was reversible. So this idea of universal quantum computer was thanks to our David Hughes in 1985. The truth tables, don't get into it, too complicated for me even. Now there are now many type of quantum computers available. Quantum annular, for example, analog quantum computer, and there many of them are giving access now. For example, talk of any big company, Google, Microsoft, IBM, Rigetti, either they have a simulator, people are making money out of it. IonQ, for example. So if you, for example, I am actually associated with a quantum aggregator in Toronto called CogniFrame, COGNIFRAME. So they have put me as their advisor, and they have brought one simulator, 100-qubit simulator, and a big Toshiba quantum computer to India, which I have access to. If you want to do a good problem, you can certainly write to me. We can carry it out. Similarly, IBM also wants to collaborate if you want to have some good problem. Okay. So universal quantum computer you can do very simple way. Now, as I told you, this non-local correlation plays a big role in this business. And this Bell state and Bell measurement is the one which played the key role. Now, it was Bell who pointed out, who passed away in 1990, that what is to quantify quantumness or non-locality. So it was done through this kind of thing. Very interestingly, he sort of generalized a measurement process due to a statistics person called Bull, B-U-L-L. Bull pointed out that if you have a two-valued object like head and tail, whose output is called 1 and -1, then in a classical two fellows are there that tossing coin, maximum could be 2. Why is it be 2? Because it depends on how many measurements he carried out. So he did it so that when it was plus it was 2, plus minus or -2. So these two-valued observables having 1 and -1 as output, like the head and tail in a coin, if two of them combine certain kind of measurements, maximum would be 2, minimum would be -2. Bell did the same thing. He took an entangled state and took these operators like sigma x, sigma y, sigma z, polymatrices, whose outputs are 1 and -1. He showed that it would be 2 root 2 to -2 root 2. So mathematically, nothing more than expectation value of two operators, polymatrices, 2 root 2 root 2 -2 root 2. In a way, it is actually used for measuring entanglement also. So this is the one which really gave a quantification of so-called quantumness or non-locality. And this measurement, the so-called Bell measurement, is the one which people talk about left and right. And if you understand it, you understand quantum computation. How do you generate Bell state? For example, through Hadamard control not, you generate Bell state. So briefly speaking, they are here. Now various properties are there. You can actually study and take the state, compute the expectation value of these sigmas. You'll find out what I was telling you. Nothing more than these vectors only. And later on, for example, in the 80s, when my teacher, Professor Greenberger in City College, Jaidinger is the Australian Science Academy president, has done a lot of experiments. This person I was referring to, Pan, in China, who is reading the quantum technology, was the student. So these three people pointed out a very simple generalization. 0, 0, 0 plus 1, 1 by root 2. And you know how to create them. That has more non-locality as compared to Bell. So that has become very famous. GAZ state, Greenberger or Jaidinger state. Many things people are using it to prove this. Now, for example, as I told you, quantum teleportation is something which is experimentally verified, which our Bennett, Brassard and company gave in 93. Using EPR, their engineers, they said, forget about all the paradox. How can you use it? Now, that is how they have used. If some of you want to know it more explicitly, if you send me an email, I'll show you the calculation. Very easy And you can really show that a state can be created at far away distance, exactly, and using something called LOCC, local observation and classical communication. To do some measurement locally at the end of Alice or at the end of Bob. So telephone line, you communicate the result, which is called classical communication. And you can actually, if you have an entangled state between A and B, like a Bell state or singlet or triplet state, you can actually create state. People have shown it experimentally. Okay. So now this is a circuit for quantum teleportation. You can, or why I'm saying this, because I'm actually introducing this rotation here. This is measurement, an arrow. So Hadamard controller, these are the state which goes in. This is a measurement, and this flow is control Z. What is control Z? If it is 1, then you apply a matrix. This Z is 1, 0, 0, minus 1. X is 0, 1, 1, 0. They are our polymatrices. Computer people call it Z, X, and Y. Okay, so these are the kind of things. Now, this was my first venture into quantum world, where my question was very simple: that if I have a quantum computer, for example, if there is a Bell state which I have created here, now if the entanglement is there or not there, I do not know. So I am using my Bell state to do some quantum computation. But suppose through measurement or through decoherence or somebody touching it, one state is gone. How long I'll wait? So we came up with a student, for example, Monu Gupta, who was a BTech student, doing his final year project. So he actually, I was very new to it. He came up, with the circuit. We checked it. That indeed, in fact, you can, through an ANSI lag, you can do some measurement, so that you can in fact check the state is there. You see, chi1 2 is here, chi1 2 is intact. You are not changing the state, but through this measurement, state is intact. So very, that is my beginning problem. Unfortunately, Professor Anil Kumar verified it experimentally later on in 2011. And we have used this idea in many, many places, even for correcting errors. So now, as I told you, when you are doing quantum computation, you have to keep in mind certain theorems. One is the U2 theorem, or no cloning theorem. Please take a look at it. So these are the very famous papers. I'll share my talk with your Professor Dr. Paul, who can share it with you. EPR paper, just take a look at it, read it. Very interesting paper. Bell's paper, you see how he has generalized this Boole's thing. And JZ state, my Professor Greenberg was the one who taught us quantum mechanics in City College. And you can see Bell inequality test is even going on, even now also. And there are certain non-locality, certain aspects which are still not very clear. And here I am mentioning Arun Pati, one of our leading researchers in HRI. Bell's non-locality can be detected by the violation of EPR steering inequality. What is this by steering? This was again due to Schrodinger. Entanglement, steering, these are the words which Schrodinger used. You will see 90, 35, 36, amazing person. Okay. Now people have, for example, recently shown that a physical object like a insect called tardigrade, a state from there can be entangled with another one. So macroscopic states inside macroscopic object can be entangled with qubit. It's a very amusing kind of thing. Okay, so I think I'll stop here. So I have 5 more minutes to go. So if you have some questions, please ask.
Thank you, sir.
Thank you.
Thank you for your valuable talk. Now, I would like to request the participant, please ask if you are having any doubt.
I think they are hungry. So, so they can ask me. If they ask me to my email, you can give them my email. I'll share my talk also.
Okay, sir. Thank you, sir.
Thank
So, from the Department of Information Technology, Tripura University, I humbly thank you, sir, for your valuable talk.
Thank you.
And thank you all the participants for joining. And the most important thing is today afternoon we don't have any session, so we will next see you tomorrow morning. And with this, I want to conclude the session here.